Now let's test on YouTube. Testing on YouTube. All right, YouTube works. Spit out this gum. Take a sip of this espresso. How's it going, Fardeen Khan? What is that? I can't see what that is. Is that like a peace sign? Message retracted. Now I can't tell at all what it is. Hello. Alright, now we just gotta wait a second here for the X stream to start, and then once it starts, we will get started. Okay, I think the X is live. So let's go ahead and start this stream. Welcome to another Hoopo stream. Today we're going to be looking at some robotics papers, which I think represent basically the state of the art in terms of home robots and also the application of VLMs and LLMs and all the kind of more recent wave of foundation models to robotics applications. How's it going, Raphael? So in case you're joining this stream for the first time, all the notes and links for the different stuff I'm going to be showing you today can be found here on this GitHub repo called Stream Docs, and you can find it for the specific date of the stream. And I write it in a European date style format, which is date, then month, and then year. So this will have all the links to all the different papers that we look at today. But we're going to be looking at 4 different papers. And here are the 4 papers that we're going to look at. The first one is going to be OK Robot. What really matters in integrating open knowledge models for robotics, and that's where the OK comes from. It comes from this open knowledge, OK. This is work mostly out of Meta and New York University. So Meta is basically probably footing the bill, and then New York University is providing the undergrads who are going to do all the work and write the paper. This was released 22nd of January 2024, so relatively recent work here. The next paper we're going to be looking at is this one here, AutoRT, Embodied Foundation Models for Large-Scale Orchestration of Robotic Agents. This comes from Google DeepMind, and this is the 23rd of January 2024. The next paper we're going to look at is from the same Google group, the Google DeepMind group, which isn't actually the DeepMind group in London. This is the DeepMind group in Mountain View, which is used to be Google Brain and used to be the Robotics at Google group. I haven't been there in a while, so obviously I don't know what the status of the hierarchies is anymore, but I actually did work with a bunch of these people, so I'm going to be a little bit biased towards the Google papers because I like literally know these people, and because of that, I have to kind of speak nicely about them. But this paper, also from Google, 22nd of January 2024. This one is not about the robot specifically, but it describes a spatial VLM, which I think is going to be pretty useful to think about where robotics goes. This one's called Spatial VLM, Vision Language Models, endowing them with spatial reasoning and capabilities. And then the last paper we're going to look at is kind of a last-minute addition. Thank you to one of our Discord members, Majetti, who found this. This one was released on 25th January 2024, and this is a paper out of Carnegie Mellon University, which is where I went to school, but I actually don't even know any of these people. And this is called Adaptive Mobile Manipulation for Articulated Objects in the Open World. So all of these papers have to do with what are called mobile manipulators. So a manipulator is basically a robot arm with a little gripper at the end of it, and then a mobile manipulator is when you put a robot arm with a gripper on it on a mobile base. So mobile manipulators are pretty hot right now, and I think just to kind of get an idea of what we're dealing with, here are the different videos that are provided for these. So this is the Meta robot, or the OK robot. And you can see here it's got a little mobile base, which has basically the ability to move within 2D flat terrain. This thing isn't going to go up any stairs or down any stairs, but it can go up and down wheelchair ramps, right? So as long as you have kind of a disability compliant space with elevators, then these robots can pretty much get everywhere. It has this arm, which is actually quite a weak arm that has some prismatic joints. Prismatic joints are the joints that kind of extend out like that. And then you have, of course, rotational joints. This one has this arm that kind of goes up and down, as you can see there. It goes up and down on this kind of stick, and it has a little parallel jaw gripper at the end of it, which just basically has two fingers that go like this, right? The parallel jaw gripper refers to the fact that the jaws of the gripper are parallel to each other, right? So they just kind of do these little pinch grips. And then at the very top of this robot, you see that it has basically a camera here. I think this is an Intel RealSense depth camera, so it's providing an RGB image, but then it's also providing a point cloud, which is the D in an RGB-D camera, coming from structured light. There's plenty of problems with structured light sensors, but the depth is quite important and required for these robots right now, unfortunately. So this camera can basically do a little bit of pan-tilt, pan side to side, tilt, and usually they don't have rotation because it's not a very useful degree of freedom. So that's the Meta robot. I think that's probably the cheapest out of all of these robots. You can really tell it kind of has, the arm is kind of low budget, kind of janky, and the whole setup is a little janky, but it's going to be cheaper. This is the Google robot, and this robot is a little bit more expensive, a little bit more clean, a little bit more polished. And here you have a video where you have a bunch of them kind of in this fake environment that they set up where there's a bunch of stuff on tables, and you can see the 10x down here means that it's sped up 10 times. So this is not in real time. This is happening at 10x speed. And robotics videos have a tendency to be a little bit gamed, you know? Like there's always a little bit of fuckery going on with robotics videos. There's generally the speed is changed. So in this video, it's actually 5x speed. So this is not real speed. You can see down here it says autonomous, 5x. That means it's sped up 5 times. So in real life, it moves very slowly. This one here, it's sped up 10 times. So it's even, robots look even faster than they really are. But also this environment isn't like a real environment, right? It's kind of manicured. You can see that they've kind of put specific things on this table that are grabbable, like there isn't any humans walking around. It's kind of a very manicured. The floor is completely flat. There's only one desk or one chair at this table, so it's not a true in the wild kind of environment. But you see that these robots also have a little manipulator. This is a more rugged arm. You see that has no prismatic joints here. These are all just 7 DOF rotational joints, so there's 7 of them total. You also have a parallel jaw gripper with some kind of compliance in it, which means that it's got a little bit of give to it. So even if it doesn't grab perfectly, it can still kind of deal with kind of a little bit of uncertainty because it deforms a little bit, right? The OK robot also has the same feature. These robots also have the pan tilt head, so you can see it has the tilt there. It can tilt up and down, and then it has the pan, which is the left to right. And the reason you want the pan tilt is so that you can VR teleop these robots. So in all of these papers, these robots are going to be teleoped, which means that someone's going to be sitting in a VR headset, and they're going to be basically controlling the robot. So for the person in the VR headset to control the robot, whenever the VR headset moves side to side, right, the head will move side to side. Whenever the headset pans or tilts up and down, the little head will tilt up and down. So generally, you can also do this, right, with your VR headset. You can also roll your head side to side, but that motion doesn't necessarily give you much benefit, so they don't have that in there. It's just a pan tilt. You see this little red button right there on the back of the robot. That's the e-stop. So pretty much every robot, especially industrial robots, will have these little e-stops so that if you see the robot attacking someone or performing some nefarious things, you can always just slap that red button and it just kills the robot. And then these robots have a little bit more of an advanced sensing package. So I think they do have a structured light sensor in the head as well, which will give you that RGBD. But then they also have a more expensive, explicit depth sensor right here, which is basically a laser-based sensor that sends out these little laser pulses and spins very, very rapidly. Right, you can see how fast it's spinning, and that'll give you a kind of denser, cleaner point cloud if you want to use that. But I actually think that those are going to go away. I think that these types of laser sensors are expensive, and point clouds are less and less useful, especially now that we have vision language models. So I can see these specific laser sensors like that kind of disappearing to drive the whole cost of the robot down. What else? One thing that you see these little robots do occasionally, which is kind of cute, is that you'll see them do that. So you see this robot in the back that suddenly raises his hand all the way up. That's basically, that's called the candlestick pose because it's just pointing straight up like a little candle. And that's usually used as a calibration or kind of a reset position. So whenever you see the little robots put their little hand up, you see now this one put its little hand up right here. That usually means it's resetting. So it finished whatever little pick and place task it wanted to do, and now it's resetting. So that's the second robot, which is the Google robot. And then the last robot we're going to look at is this one here, which is the Carnegie Mellon robot. This is probably the most expensive robot just because it's a bespoke kind of prototype. This is like a robot arm here, which is just like an off-the-shelf robot arm that you could buy, and they put it on a mobile base. So this is like they literally just glued a robot arm on a mobile base. And in the paper, they do mention that it's a $20,000 robot, 20,000 USD. So if the most expensive bespoke one is $20,000, I would guess this robot here probably around $10,000 if you were to manufacture these at volume. And then this robot here, which has kind of the cheapest components, probably low single-digit thousands if I had to guess, like $3,000, maybe $4,000 if you really want to stretch it. So we're getting close because these robots are capable of doing pick and place in a home environment. They're capable of doing these tasks, and for a couple $1,000s, I think a lot of people would be interested to have these at home. So if I had to guess, I feel like we're going to have these type of little robots in our house within maybe not the next year, maybe not the year after that, but by 2025, 2026, I think you should be able to purchase a little robot like this that will go around your house, maybe take things out of the dishwasher, maybe put things in, put the little dog toys back in the bin, stuff like that. You know, pick up things that are on the floor, bring you a drink while you're watching TV or something. So pretty cool stuff. Robotics is finally happening. You know, for decades, the robotics world was just this world of demos where you just kind of did one-off demos, and you know, it never really felt like you were progressing. But now these language models and the vision language models have really kind of 10x'd and really solved all these problems that were very, very hard to solve before. And the hardware has kind of been there all along. You know, the hardware has existed in a state where it's been usable for a long time, and it was really just the software that was limiting us. So now that we have kind of a step function improvement in the software, we can basically get these things going. How's it going? 2ARX and 87GN. Okay, so that's the three different robots that we're going to be looking at today. You can see that this robot isn't doing any type of pick and place. It's basically just opening doors. This robot is not a general purpose robot like these ones here. This is more of a kind of a traditional kind of reinforcement learning, single task based robot. So we'll learn about it more in the paper. All right, guys. So those are the three different types of robots. And let's start by looking at the paper of the OK Robot. The OK Robot is an open knowledge robotic system which integrates a variety of learned models. right, integrates a variety of learned models. There's going to be several different models being used as modules within a larger system, right? So you're going to have a vision pipeline, you're going to have a navigation pipeline, and that's the more traditional way of doing robotics, and the way that it's always been done is you kind of separate all the problems into these separate systems, and then you solve each one independently, right? So you solve vision separately from path planning, and you solve manipulation separately from navigation. But I actually think it's going to move in the opposite direction, and I can see a world where we just have one kind of monolithic vision language model that does everything. So I feel like the way that foundation models are going, we're going to kind of move away from this modular kind of different subsystems, and we're going to move to just one, but I think we're still a couple years away from that. Using open world knowledge models such as CLIP, this is an image and language embedding model. LangSam, this is a segmentation model, the segment anything model. AnyGrasp, which is a grasp generation model, which basically picks grasp positions given an image and some information. And then OWLVIT is a object detection model. So OKRobot achieves 58% success rate across cluttered home environments. These percent success rates don't really mean shit. You know, it's kind of, you decide what the success rate is going to be by picking the test, and the test is not very reproducible. So anytime you see like a picking or a grasping success percent in a robotics paper, it's almost meaningless because no one else has the opportunity to evaluate their particular robot on that thing. So don't worry too much about these percent numbers. Kind of make your judgments more so on the videos that you see. Okay. How's it going, Khalil? Remarkable progress has been made in recent years in the field of vision, language, and robotics. We now have vision models capable of recognizing objects based on language queries, navigation systems that can effectively control mobile systems, and grasping models that can handle a wide range of objects. Despite these advancements, general-purpose applications of robotics still lag behind, even though they rely on these fundamental capabilities of recognition, navigation, and grasping. And this is really, recognition is the one that has really improved with the deep learning. In this paper, we adopt a systems-first approach to develop a new robotics framework by combining VLMs for object detection, navigation primitives for movement, and grasping primitives for object manipulation. OKRobot offers integrated solution, pick and drop operations without requiring any training. So it's kind of zero shot, which is, I think, the way that we're going to be able to have robots very easily. And the robotics problem now is not really a kind of problem where you have to improve any one of these things fundamentally. It's really become an integration problem where you just have to take all the different parts and integrate them together with a piece of hardware. And that's why you're seeing so many different groups kind of get to the same state of the art very, very quickly, right? So there's no secret sauce that any of these companies has. The secret sauce is just language models and vision language models, which everybody kind of has access to in some shape or form. They're going to be testing this out in 10 different real-world home environments. Okay. We're going to skip most of the introduction section here and just get to the very end of the introduction section here, where they basically go through the bullet points. These are going to be a summary of all the different things that they accomplish in this paper. So maybe one thing here, the NeurIPS challenge for open vocabulary manipulation registered a success rate of 33%. So this is what they're kind of claiming for their state-of-the-art, right? State-of-the-art in open vocabulary mobile manipulation. But as I said before, that's kind of a little bit bullshit because no one else is competing in this NeurIPS 2023 challenge. So I bet you this robot here would perform quite well, but it's not performing on that. This robot here could also perform quite well. So this whole state-of-the-art, I don't buy it, right? Okay, but here at the end, pre-trained VLMs are highly effective for open vocabulary navigation. So a pre-trained vision language model is a vision language model, right? Like the one that you access or the one that you interact with when you're using images with GPT for vision, right? It's what it basically does is it consumes that image and puts it through a vision transformer to convert that image into basically these vision patches, right, which basically are converting that image into a sentence of visual tokens. Those visual tokens are combined with whatever language tokens you have for a question or some kind of query, or like, is there a dog in this image, or how many how many bags of Fritos are there in this image, right? Move the soda can to the box. Whatever natural language query you have with that, the VLM will then respond in language. Current open vocabulary vision language models such as CLIP or OWL-VIT offer strong performance in identifying arbitrary objects, right? That's the open vocabulary, where it's not limited to some specific category of class or category of objects, which is the case of more traditional object detection pipelines, which basically are classification models that are limited to maybe 1,000 different categories. But in open vocabulary, which you're getting for free because of this CLIP model here, you can basically query for arbitrary objects. Enable navigating to them in a zero-shot manner. You can also use VLMs for navigation. Pre-trained grasping models can be directly applied to mobile manipulation. So similar to VLM, special-purpose robot models pre-trained on large amounts of data can be applied out of the box to approach open vocabulary grasping in home. Grasping is the kind of like mobile manipulators can be broken up into these two problems, right? You have the manipulation or the mobile or navigation problem where you're in this specific part of a home and you basically want to move to the part over there, right? That's a navigation problem. And then you have the actual grasping problem, which is moving your end effector to the specific position and grabbing, right? Moving that little gripper, deciding what the commands for each of the 7 different joints in the arm are going to be doing. And there's models to do that, what they call here pre-trained grasping models, but I feel like that's probably going to be combined. To me, it's like there's going to be one VLM that does both of these things, but right now you see separate stacks. How's it going? No free will. Feel free to interrupt me with questions. You know, I'm kind of just blasting here on these robotics stuff, but if you guys have any questions about anything robotics flavored or where any of this is going, definitely interrupt. Okay, how components are combined is crucial. Given the pre-trained models, we find that they can be combined with no training using a simple state machine model. And I literally did this myself, right? So I have a little humanoid robot here, and I did a project where I did zero-shot humanoid robot, and what that means is that I used a vision language model and a large language model in combination with a simple state machine to basically do little things with this humanoid robot. But I did not have to fine-tune the VLM or the LLM. I used them basically zero-shot, and they're able to basically, with a cleverly made prompt, do everything that you need to do. So you don't even need to fine-tune these VLMs and LLMs, which is very powerful. Using heuristics to counteract the robot's physical limitations can lead to a better success rate in the real world. Several challenges still remain. Given the immense challenge of operating zero-shot in arbitrary homes, OK Robot improves upon prior work by analyzing the failure modes, and we find that there are significant improvements that can be made on VLMs, robot models, and robot morphology that will directly increase the performance of open knowledge manipulation agents. Okay, so basically, in order to get to that home robot in your house that can zero-shot find your laundry room and take everything out of the washer and put it in the dryer, right? aka operating zero-shot in arbitrary homes based on open vocabulary commands, you're going to need to improve a couple different things here. You're going to need to improve the vision language models themselves, which I think is going to happen no matter what, right? There's going to be a ton of progress by the time you get to GPT-5, GPT-6, GPT-7 vision language models. They're going to be multimodal, and they're going to be probably 2, 3, 4 times better than what we have now. So I think that'll come for free. Robot models, I feel like those will probably disappear. Honestly, I feel like the VLMs will just become so strong that you don't need these kind of explicit robot models. And then finally, the robot morphology, I feel like we're already there. Like I said, the robot hardware was way ahead of the software for a long time, and I feel like if you just have a way better vision language model, this should be more than enough, right? You don't really need to make a much better hardware platform. If you just make this one smarter, then it should be enough, and then you can just focus on trying to make it as cheap as possible, right? And that's maybe where these mobile manipulators will win. You know, there's a lot of competition right now in the humanoid robotics world where people are basically using full humanoids like the Tesla Optimus robot, but the full humanoids are a little bit more complicated and more expensive, right? They have twice as many arms. They also have much more elaborate hands, which have all kinds of little actuators in them, right? So I think these single-armed mobile manipulators might actually edge out the humanoids, not because they're more powerful, but because they'll be basically significantly cheaper, right? So still not entirely decided whether we'll have humanoids in our home or whether we'll have these mobile manipulators, but I think it might come down to a cost situation, and if it comes down to a cost situation, these little single-armed ones are going to be cheaper. Okay. What else? Technical components and methods. Okay, so here they basically describe all the different parts of the stack here. They have a open vocabulary object navigation, right? And in order to do this, they have a pre-mapping phase where the home is scanned manually using an iPhone. So this is a little sucky, you know. Look at that. Okay, so basically here in this paper, you see here how they have basically this 2D top-down view of the entire room. That's not a navigation map that was built by the robot. That was a navigation map that was built by the human. So there was a human that basically went through with an iPhone and basically scanned the entire room and then created this static map, right? So there's a lot of issues with that. One is that now you have a static map, right? So in any kind of SLAM problem, SLAM being simultaneous localization and mapping, you want to be able to have a dynamic map that is updated kind of constantly so that you can move things around in this room without completely messing up the map. But in this paper, they do not do that. It's a static map, so that's a little bit unfortunate. For detecting objects, they use the OWL VIT as the object detector. They apply it on every frame, so every single RGBD image that's coming from this head camera, and extract each of the object's bounding boxes. Old school object detectors work with a little bounding box, so they basically get a little square within your picture that defines the exact object, and then you can kind of crop that out. The clip embedding is basically they feed that specific cropped bounding box into a clip model, and the clip model will give you an embedding that represents kind of the semantic content of that. Pass them on to an object memory module for our navigation module. So they have basically a module that stores all the different objects that you've seen as you're navigating around, right? And those are stored as kind of semantic concepts via a clip embedding model. They further refine the bounding boxes into objects masks with the segment anything model. So whenever you use an object detector to get a bounding box, you're going to have a bunch of kind of leftover stuff on the side. Let me see if I can show you guys what's going on. Yeah, so right here. This is a different paper, but it kind of explains why you would need the bounding box. So you see here you have a picture with these 3 kids, and then you use a bounding box model, and you get these boxes. But now there's a little bit of slop, right? It's like you're getting the kid, but you're also getting the background, you're getting parts of the foreground, and you want to basically, if you're going to feed this into clip, you want it to be a very clean kind of semantic vector. So in order to do that, you take the bounding box, you segment out the basically the part that you're interested in with the segment anything model, and then you feed only the stuff that was segmented out into a clip in order to get a very clean semantic vector. Question from No Free Will. I think people might freak out from humanoids, but not so much from robots that don't look human. I would personally prefer having a house for a robot that doesn't try to look like a human. Yeah, maybe. I think it depends, because you could also make the case the other way, right? Where people would want the humanoid just because it's a little bit cooler, you know, but I don't know. I think these will be so cheap that we might end up with mobile manipulators instead of humanoids. Okay, object-centric semantic memory. This is the kind of storing objects. What else? Yeah, this is kind of also not great. This meta paper does a bunch of things that are a little bit primitive, but they back project in the real world coordinates using the depth image. So because their RGB image is coming from a RGBD camera, for every single pixel they have an associated depth value. So once they bounding box and then segment out some specific object, they can then say, okay, what specific pixels in the depth image correspond to that, and I'm going to basically, because I know the world coordinate position of my head, I can basically then project forward and then get an estimate of the position of this object in real world coordinates. But the problem with that is that, one, the depth is noisy, and then two, if you miscalibrate the camera, the head camera, then you can basically be off. So this type of way of getting an actual position for an object is a little bit primitive. This is the way that you kind of used to do it, and there's plenty of problems associated with that. So I don't feel like this is going to be the way that we do it in the future. I think the way that we do it in the future is going to be the way that they do it in this paper. Maybe that's a good transition into this paper. We're going to jump around in these papers a little bit, but hopefully I try to paint a coherent picture here for you guys. Kalina saying what is probably the darker reality of humanoid robots is that what if it looks like an anime girl, and there's a truth there, right? That unfortunately people are going to want to fuck these robots. That's just the way that humans work. You know, we're primates. We have weird urges, and you know, nobody wants to do anything with this type of robot. But if it looked like a human, you know, people are going to do what people are going to do. So I don't know. Kind of a dark world, right? All right, back to this. So we don't want to be relying on depth sensors to basically get the relative position of things in the world so that we can grab it, right? And this is a problem that these researchers here attempted to solve by fine-tuning a vision language model to basically give you or have notion of depth. So for example here, if you just feed this image and then this prompt here into GPT-4V, which is basically the state-of-the-art vision language model, and you say, okay, blah, 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 do you think I can go between the robot, or between the table and the chairs, right? Do you think there's enough space for a 1 meter robot to go between that? So you're asking it a very precise kind of dimension question. So GPT-4V is not going to be able to tell, right? It doesn't really know. It can give you like a kind of idea like this. It appears that the sofa and the table are quite close. There may not be enough space. But the spatial VLM, which is the VLM that they fine-tuned for this paper, can basically answer that much more precisely, and it makes a very accurate guess here. It says, I think that the distance between the couch and the chair is 1.56 meters, which means that you should be able to go in between there is if you are 1 meter wide. Right, so another example here, GPT-4V, what is the closest can to the yellow finger? GPT-4V kind of gives you a little bit of a nonsense units here, approximate distance of 110 units, but the fine-tuned spatial VLM makes much more accurate guesses, 0.5 meters, 0.59 meters, 0.21 meters. So this is pretty good, right? And this is just a first try, which is why I think that we're going to see depth and explicit depth disappear, right? We're not going to need to do any kind of RGBD and then segmenting out and then using the back projected depth pixels into the real world coordinates and then use that as the object position, right? We're not going to be needing to do, we won't need to have any of these types of laser scanners, sensors, explicit depth sensors on these robots, because this type of stuff is going to be very, very good, right? Just using a fine-tuned vision language model that just only uses the RGB camera and then use that to get the depth information that you need. Okay. The way that they do this, there's a lot of crap here. You don't really need to know most of this, but this is the way that they train it is they train it with a synthetic data set. This figure 2 here shows you how they collect or create the synthetic data set that is then used to fine-tune the vision language model. So first they start with a bunch of what they call noisy internet images, right? So just a bunch of random images from the internet. They semantically filter them in order to only keep images or only keep photographs. So you can see they get rid of this Doraemon picture. They get rid of this 2D picture of this apple juice. So they only want photos. Okay, once you have the photos, then you can basically bounding box, and then you can do this metric depth estimation here. This is the result of a monocular depth estimation model. So monocular depth estimation basically tries to give you a depth image, which is what you would get from a depth camera, but it does so without any depth information, right? It's just guessing. It's guessing from seeing hundreds and hundreds of depth images that it's been trained on. And these monocular depth estimation images, or monocular depth estimation models, are very, very good. They're starting to get like good to the point that you can basically use them to do, I guess in this case, fine-tuning a vision language model on them. Here you have segmentation, coordinate canonicalization. This is how you can basically make the metric depth estimation not just kind of normalized, but specific to some specific unit. Here we go. Ambiguity resolution. Lift the 2D images. We avoid asking ambiguous questions by clustering object captions using clip similarity score. So they're basically using clip to basically get semantic embeddings, semantic information for each of the different things that were detected by the bounding box, and then use that to basically create these fake Q&A questions where they're maybe like, how far away is the boy from the girl on the left? How far away is the cupcake from the table? And they basically just create a giant synthetic data set of these spatial questions and answers, and then fine-tune the vision language model on that. Okay, I think that's mostly this paper here. But this thing works pretty well. So they have some examples down here. So example question pairs from the spatial VQA qualitative and then quantitative. So quantitative is more precise. How far away is the tie from the left of the cell phone? About 0.2 meters. Determine the distance of the fence from the giraffes. About 5 meters. Could you provide the distance between the sign and the motorcyclist? About 0.5 meters. Right? And all of these are pretty good. So here with the robot, what is the height of the bag of chips with respect to the table? About 6 centimeters. How much distance is the red apple from the can on the table? 20 centimeters. So, I don't know. This to me paints a pretty simple picture, is that spatial VLMs or VLMs can be fine-tuned to be quite accurate and be very good at providing depth information. So if you're very good at providing depth information, you don't need to be doing any of this crap with depth cameras, which means you can get rid of the depth cameras, which means all you need is an RGB camera, which will mean that the whole robot will be way cheaper. Question from 87GN. Does all of this run on the cloud, or does it run on the local robot? You can do both. So for example, this robot here, the Carnegie Mellon robot, has a computer on board. So it has an NVIDIA Jetson computer. Right, so it has an onboard computer that does all the calculations itself. The NVIDIA Jetson computer has a little GPU in it, this one here. So you can do all the compute on the robot itself. But this robot here does not do that. This robot here uses an API. So this robot, which is the Google robot, it doesn't do any of the processing or compute locally, right? It basically pings via an API, some server sitting on some Google Cloud somewhere, and then it gets the response back. So what are the benefits and the pros and cons of doing that, right? So the pro of having all the stuff locally, as in this robot, is that it can all stay on the robot, right? You don't need to be connected to the internet, and it can run everything on the robot, which is good for privacy reasons. And maybe that's it. It can operate in a geomagnetic storm, or I don't know, for some weird reason you can't connect to the internet. That's basically it. But what are the negatives of onboard compute? The negatives of onboard compute is you're limited to that computer, right? So if the models keep getting bigger and they keep getting smarter, at some point they're not going to be able to fit on this little computer. So then what are you going to do? You're just going to have a shitty robot, right? It's a lot more convenient if the model is not on the robot, so that if GPT-5 gets released, if GPT-6 gets released, if GPT-7 gets released, your robot just gets smarter and smarter every time because it doesn't need to run it on the robot, right? The GPU, the hardware on the robot is no longer constraining the types of models that can be run, right? It can run anything just through a software update. The negative to running via API like that is, one, there's the latency issue. You always need to be connected to the internet, and it's also not going to be as private, right? So it's basically going to be sending pictures of your home to some Google Cloud. I'm sure they'll wrap it. They'll do like end-to-end encryption, and they'll give you some kind of guarantees that they're not going to be training on the data, but it is what it is. And then there's also the speed. I mean, that's also why they operate a little bit super slowly, is because, this is not like an autonomous vehicle where you need to be able to react in like milliseconds. This is like you can operate much slower, maybe at the rate of 10 hertz, right? Like 10 times a second, or even 1 time a second, 1 hertz. And that should be probably fine to do what you need to do. So if I had to bet money, I think that the compute is going to be running via API. So I think that when you have these robots in your home, I don't think you're going to be it's going to be a situation where you have a NVIDIA Jetson kind of onboard edge compute, as it's called. Instead, I think it's much more likely that these robots will be running stuff in the cloud. Wonder what GPT-5 robot. I'm looking through the questions here. Depth estimators are very good. Good paper about this lately. Yeah, the depth estimate, it's basically a solved problem, right? So it's like this monocular depth estimation is effectively, I don't want to say solved problem because, there's still a little bit of juice to extract, but they're very, very good. Like, I saw that paper too that you're mentioning, Rafael, where they're basically depth anything. It's like we're getting to the point where you feed it any kind of image and it can basically almost get you a perfect depth map. And you don't even need that model, right? So you're not going to actually run this monocular depth estimation model on the actual robot. You're going to use it to create a synthetic data set, and then you're just going to fine-tune your vision language model on that synthetic data set with very precise distances. So at the very end, what your robot is going to be running is going to be running this VLM. It's only going to be running a vision language model. It's not going to be running these monocular depth estimation models. These monocular depth estimation models are only going to be used to create a synthetic data set to then fine-tune these VLMs. Okay. Yeah, so now we're back in the Facebook one, the OK Robot paper. So we were talking about how they still use this kind of older way of basically using explicit depth to basically place everything in the real world. They also have this negative here where because they're using a pre-scanned world, right, that's been scanned beforehand, it's a static world, which means it's not being updated. So that's obviously not going to work, right? You need to be able to basically update the map constantly, right? The robot needs to be able to, like, every time it goes through your house, it's basically constantly rebuilding this map of your house. Here they pretend that it's an advantage. They say our map can be low resolution. Low resolution maps are not an advantage. They're a disadvantage. It's a bad thing that you have a low resolution map. But, they pretend that it's an advantage here. Here they're saying we voxelized the point cloud to a 5 centimeter resolution. A voxel is basically like a little square. You could think of it like the minimum unit of your map, right? So your map has some minimum resolution, right? Some pixel. What is the size of the pixels of your map, right? So here they're saying that the voxel resolution of the map that it's operating in is 5 centimeters, which is a lot. That's basically the difference between making a grasp and missing a grasp. 5 centimeters is a lot. Okay. The navigation. So they describe the navigation. They even have some math equations here, but these are like kind of a little bit unnecessary, right? All these math equations are really representing here is that there's some point that you want to navigate to. There's some obstacles, and there's some object, right? And then it's basically you have 3 different kind of. You could think of it like the path that you're going to take is going to be basically accounting for a couple different things. It's going to be trying to minimize the distance to the final object. It's going to be trying to minimize the distance to the target object, and it's going to try to stay away from obstacles, 40 centimeters away from the obstacles, and it's going to try to balance all these things. So it's basically using this heuristic here to basically navigate like this, right? And pick these navigation points and then move across those. So I think this is like old school navigation. So old school navigation, right? You basically create a plan. So a plan is a thing that you're going to execute on, right? So you basically, the way that robots worked and is that in order to move even the arm itself or the base itself, it's not deciding at every single time by feeding in the current state into a model or a neural network and then outputting the wheel commands or the arm commands, right? The way that these robots work, which I actually think is going to disappear, I think this is kind of the more old school way of doing, is that you build a plan and then you execute on that plan, right? So they're basically the little robot base, this little mobile base here that moves around. It's not being controlled directly by a deep learning model. What it's doing is the deep learning model, and it's not even a deep learning model, right? Because they're basically just using this heuristic here, is picking out a set of points, putting those on the map, and then the base itself is just basically hard code, like position PID controller, just going from here, then to here, then to here, then to here, then to here. And people used to do that with arms too, right? So every time the arm would move, it was just the motors themselves were just moving to these predefined points that were the result of a path planning step. So you were basically always doing this kind of like path planning and then execute, and then path planning and then execute. But I think we're actually going to move to a world where basically it's real time kind of actions, right? Where basically rather than your models outputting some kind of plan and then you execute that plan, the models are outputting the actual command that you're going to be doing at that specific time step, right? So the model is running every single time step. That seems kind of crazy, but I feel like that's how you're going to actually get the kind of reactivity and the kind of dynamic nature that you need, right? Because the problem with these plans is that they assume a kind of a static nature, right? So let's say that you create this plan and the robot starts moving, but then a human kind of appears out of nowhere and then moves right here, right? What would happen is that the robot would have to stop. It would have to realize that there's a human. It would have to create a new plan, and then it would have to execute on that new plan. That's way too many steps, right? It's better if the vision language model is basically getting queried 10 times a second and it's saying, what do I do now? 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 And it just decides these kind of like micro movements and directions at every single time step. It's a lot more inferences, right? It's a lot of inferences, but I feel like that's going to result in much more kind of reactive behavior that is going to be, I think, more powerful. So, that's my comment on that. We build a 2D 10 by 10 centimeter grid of obstacles over which we navigate using the A-star algorithm. Again, I just feel like this is very, very old school. It's not even, because it's also a static map, so it's like doubly bad. So, RGB head camera, parallel jaw gripper. We prefer horizontal grasp because they are robust to small calibration errors, while vertical grasp need to be quite point accurate. Here they're referring to like a horizontal grasp is like this versus a vertical grasp is like this, right? So the horizontal grasp, you can have a little bit of slop and still get it correct, right? If you do this and you go like that, you still get it. But vertical grasp, you have to kind of get it perfect. So the way that they're going to be getting these grasp positions is they're going to be using this any grasp model. This is like a model that basically gives you these proposals, right? So here's your robot view. It's looking at this counter here. There's a bottle on that counter. You can get the segment anything model to basically segment out the bottle itself. You can then use that in conjunction with your explicit point cloud in order to get a bunch of depth points. So you have basically an idea of like where this bottle is. The AnyGrasp is going to basically then give you a bunch of possible grasp positions, right, which are basically similar to this, right? They're basically like, here is the final position that your gripper should be at in order to execute this grasp, right? It's going to basically create these final positions, and then you're going to filter them out to only the ones that are in this bottle, and then you're going to basically pick the highest scoring one out of these AnyGrasp. But kind of, as I said, with pretty much all the things in this OK Robot meta paper, this is very old school, right? This feels like what you were doing in 2015, right? Like we were doing these kind of techniques in 2015 for robotics, and this is not what modern robotics is going to look like. This is kind of the piecemeal, kind of like separate modules, like break up the problem into like 17 different sub-problems and then solve each of the sub-problems. I just don't feel like this is what we're going to be doing in the future. This is kind of old school robotics, right? The more you break up your problem into little sub-problems like this, the more surface area you leave to basically have errors creep in, right? You can have an error creep in here. You can have an error creep in here. You can have error creep in here. You have an error creep in here, right? I think it's a lot easier to basically just have a vision language model that just sees from an RGB camera, and then the vision language model literally outputs joint commands. It's literally telling the individual motors at each of the different joints of the robot what to do at every single step. Sometimes that's called visual servoing is the word for that, but I feel like that is a much simpler and much more powerful pipeline than what you see here, which is this kind of more explicit, old school, kind of like break it up into pieces pipeline. Placed at the base. So here they're basically saying that it has a little robot. It has a little like Roomba base. So here it looks like they plug it into the wall, but I think that whenever they sell you these things to put it in your house, it's going to be similar to a Roomba where there's going to be like a little base where it can sit there and charge, right? Our system takes under 10 minutes on average to complete the first pick and place drop task. So that's just kind of like advertising that this is a sped up video, right? 4 times speed up. So really this robot is operating extremely slowly, but there is solutions to that. So one kind of clever solution that I've heard to the robot operating slowly is that the robot is not going to be doing things during the day, right? So you envision your home, right? And you have one of these little robots in your home, right? You don't want the robot moving around when the humans are there, right? Because whenever the humans are around doing things, the world becomes very complicated because you have to make sure not to hit the humans. The humans might be moving things around. You're going to lose track of things. So actually the best way to solve this, right, is to actually have the robot do things at night. So I think what will probably happen is that these robots will just sit in the corner completely still, not doing anything all day. They'll be charging the battery. And then when you go to sleep, they will spin up, and then in the dark, they will clean your entire house. So while you're sleeping, they'll be sitting there in the dark, very, very carefully, right, very, very slowly going, grabbing a thing, very, very slowly moving over here and putting the thing over there, very, very slowly going, and then taking everything out of the dishwasher and putting in the thing. So, right, because they're going to be doing it in the dark at night, they can be very slow. They can be very meticulous. They can be very careful, right? They don't have to worry about the human bumping into them or changing things or moving things. So that's actually another prediction here, is that I think that these robots will actually operate in your home at night. So they'll be like kind of like little house elves, you know? They'll be working when you don't see them. Okay. Let's see what else. They do some experiments here. What do we got? Samples of failed or ambiguous language queries. Samples of failed manipulation. So you see this image here. You see how like there's like weird white holes in it. So this is the result of basically taking an RGB image and then basically projecting it using the depth image. So the depth image is aligned to the RGB image, but then when you basically project it into the world coordinate frame, there's going to be the parts that are not visible by your depth camera are basically going to result in these kind of like tears, which is just another problem with depth sensors and why we shouldn't be using them. Robot has a 2-pound payload limit. So what they're saying is that this robot, which is the flimsy, this is the flimsy OK robot, meta robot, right? It's not very strong. And like that little gripper is pretty shit. This little prismatic joint with the little rotating, like this thing can't pick up anything that's bigger than 2 pounds. So that's an issue, right? And they say we need kind of a robot that can pick up something a little bit heavier. The Google robot has a little bit bigger of a payload. I think they say it's about 5 pounds somewhere in this paper. And then this one here, right, this is an industrial robot arm, so this one has a much more robust payload. This one also has something like a 5 kilogram payload, which is quite big, right? 5 kilograms. Maybe it can't move the dumbbells that you have in your home gym, but pretty much anything you put in your dishwasher it can pick up. The robot hardware or the RealSense camera. The RealSense camera is the RGBD camera that's sitting here, right? Right on the head of this. This is the RGBD RealSense camera. And this is the problem, right? Is because they're doing this explicit depth and using that to do this with this GRASS proposals and the navigation too, right? If you miscalibrate, and all these cameras, it's not like you miscalibrate at the beginning and then you're, oh wow, okay, I just need to calibrate it. It's the calibration over time deteriorates, right? As you move around, the camera is vibrating, and it's kind of like losing its tilt. It's losing its position a little bit. The gripper's losing its position every little bit. So this miscalibration issue has always been a kryptonite for robots that relied on these kind of piecemeal kind of subsystem type designs. Whereas I think that robots that use a foundation model like this, a vision language model, to do kind of visual servoing, they're way less sensitive to calibration errors because they're basically predicting every single action from scratch, basically at runtime. And if the camera moves, then it just changes a little bit. But these type of robots are a lot more sensitive to the calibration mistakes. So that's the Facebook paper, which I think is, a little bit more academic, researchy, kind of like hobby. The pipeline is a little bit old school. They still use a bunch of different subsystems, and the robot is kind of the shittiest quality out of all the robots. Now we move to the Google robot. I think this one is a lot more professional. This is a higher quality robot. They do it with many more robots, and the stack that they use, the software stack, I think is also more indicative of the type of software stack that we're going to see in the future. So, let me take a sip of this coffee and then we'll read this abstract. Intel discontinued RealSense, I thought. Yeah, the quality of the Intel RealSense cameras has pretty much always been shit, but for some reason people still use them because all other depth cameras are pretty shit, and the RealSenses are really cheap. But as I keep saying over and over again in this stream, I think we're going to move away from them. I don't think we need these RGBD cameras anymore. I think the vision language models are going to be able to do they're going to have such a good intuitive notion of depth, and by using them in a kind of a visual servoing style fashion, you're no longer going to need these depth cameras. And then as soon as we can do it without depth cameras, they're going to disappear. No one's ever going to mention depth cameras again. And we're not going to need these kind of LiDAR sensors either, right? So it'll be way cheaper if you just have a bunch of RGB cameras on your robot, because those are very cheap, because those are the type of cameras that you mass manufacture for cell phones. Okay. Foundation models that incorporate language, vision, and more recently actions have revolutionized the ability to harness internet-scale data to reason about useful tasks. However, one of the key challenges of training embodied foundation models, so foundation models that are embodied inside a robot that have a body, is the lack of data grounded in the physical world. In this paper, we propose AutoRT. This is Auto Robotic Transformer. This group has been kind of publishing a bunch of work, so this is really just the latest in a whole slew of work. So they had RT1, I think they have RT2, now this is AutoRT. Leverages existing foundation models to scale the deployment of operational robots in a completely unseen scenario with minimal human supervision. AutoRT leverages vision language models for scene understanding and grounding, and further uses large language models for proposing diverse and novel instructions to be performed by a fleet of robots. So this is kind of the pattern that you're seeing now, and this is also the pattern that I used on my robot. So I used a language model as kind of like the brain, as the highest level, kind of like, what am I actually doing? What should I be doing, right? Like kind of like the path planner at the highest level of the state machine that's actually deciding what the robot does based on whether you're giving it commands or what it's doing. People are still using these vision language models only as a kind of vision stack, right? So the vision language model in these papers is really only being used to basically describe the world, right? Scene understanding. But then there's a language model that's sitting on top of that that's using the input from using the state of the robot, using the output of this vision language model, and then combining all of that with the human task and maybe any kind of historical kind of like stuff in some kind of RAG type framework, and then combining it all together. So I think that's going to go away. I think that eventually the VLM is going to kind of swallow everything that the LLM is doing, right? So right now you're seeing the LLM and VLM kind of as different parts of the stack, but I think eventually the VLM will kind of subsume everything that the LLM is doing here. And you'll just have one VLM that basically does everything. Guiding data collection by tapping onto the knowledge of foundation models enables AutoRT to effectively reason about autonomy trade-offs and safety while significantly scaling up data collection. Effectively reason about autonomy trade-offs and safety. So basically, because these large language models are kind of like AGI, right? And you can ask them kind of generic questions. You can start asking them generic questions like, "Hey, is it a good idea to pick up this knife?" And the LLM will actually give you an answer to that. We demonstrate AutoRT over 20 robots across multiple buildings and collecting 77K real robot episodes via both teleoperation and autonomous robot policies. So first of all, it's not exactly 20K robots. So they actually have 53 of these robots, right? So later in the paper here, they do mention they have 53 robots total, but they only use 20 at the time. So basically the most that they ever had kind of working at one time was 20, but they have over 53 of them. So that, in a way, is telling you something, right? Because if the peak load is only 20 robots, but they have 53 robots in total, that kind of tells you that the robots are only working 50% of the time, less than 50% of the time, which means that there's stuff here that they're not telling you, right? They're basically, the robots either break down or they can't be trusted to just be left alone, or whatever API that they're using to control these robots, it has a limited amount of they couldn't have all 53 of these pinging that API continuously, right? So there's some reason why they're only using a small subset of the total robots that they had, right? If these robots were working perfectly, they would just be working all day, right? You would have all 53 of these robots just constantly doing shit, but the fact that they have a much smaller subset of them doing things is indicative of the fact that these robots are not quite ready to be kind of fully autonomously operating. 77,000 new episodes. So one episode is like basically, you could think of it like one task, one kind of like move over here, pick up the thing and put it down there, right? And if you remember from our little video, right, you see that when they put their little hand up, that's the end of an episode probably, and then it starts a little new episode. So you see, puts the hand up, and then it does like a little thing, and then it's done, and then it puts his little hand up. Right, so that's basically one episode, and they did 77,000 total episodes over using these 53 different robots. Okay, but the other thing that's worth kind of thinking about here is this idea of teleoperation, right? So teleoperation, right, here in this figure here, you see teleop, and then there's a little human there. So basically, a human can control these. Right? There's a human, and you can wear a little VR headset and then basically be in this robot, and you can move the little gripper, and you can click to grip, and you can pick it up and then put it down, right? And the way that these robots are going to end up being kind of deployed in the real world, there's likely going to be basically this idea of like fleet navigator or fleet kind of managers, right? And what that means is that you're going to have basically many, many robots and then one human that controls those many, many robots. So in your house, you're going to have a robot, and it's doing this stuff at night. And sometimes when it's doing stuff at night, it'll run into a situation where it doesn't know what to do. And it's like, okay, I kind of got stuck here. I tried to pick up this weird bespoke mug that this person owns, and I'm having a hard time picking this mug. And it's going to basically ping and say, okay, I need a human to help me with doing this. And then the human, who's going to be probably working in like Nigeria or some super low cost of living area, is then going to basically spawn into that robot via a VR game, pick up that cup, put it in the thing, and then end that particular episode. So the way that this will work out is that the very first systems, right, they'll probably be humans teleoping maybe 20% of the time, right? So maybe if you're one of the rich people who buys one of these robots as soon as they become available, more than 20% of the time, the robot in your house is going to be operating via some teleoperator that is working from Mexico, right? But over time, as these robots get smarter and smarter and more capable, the percentage of that teleoperation time is going to go down. So rather than a human operating at 20% of the time, it's going to be 1% of the time, and then 0.1% of the time, and then 0.01% of the time. So that's kind of a way to smooth the transition from the robot not being smart enough to eventually being able to do everything, is that basically you always have this ability to fall back on these teleoperators. And that's already being used in, for example, the robot delivery. These delivery robots here, right? They do the same kind of thing where these robots are not operating autonomously all the time, right? A lot of times, if they run into a situation where they don't know what to do, a human teleoperator can remotely control the robot, get it out of that situation, and then put it back in autonomous mode. So the idea is that you basically start with the humans remotely operating these things a high percentage of the time, and then you start accumulating more and more data, and you get better and better at kind of solving these issues. And then eventually you have one human teleoperator that's managing a whole fleet of like hundreds of robots, right? Because it only needs to remote teleop a very small percent of times. But they're going to be doing that with these as well. So it's going to be a little creepy, right? It's going to be a little creepy when you wake up in the middle of the night and your robot is trying to take things out of the dishwasher, and some random person is actually teleoping that robot from probably a third world country, and you sit there and you wave at it, and the little robot waves back at you, and you're like, oh, wow, that's kind of cute. And then little do you know that there's some guy sitting there in a VR headset who's like looking at you, like getting a glass of water in the middle of the night. So kind of a weird future, right? Where we basically have humans operating robots in our houses. All right. What else? Large fleet of N robots. You have these policies, right? So a policy is basically a neural network that produces an action given a state, right? This is like kind of a reinforcement learning terminology here. So you have human teleoperator is performing a policy, right? And you can behavior clone to that specific teleoperated policy. Right? Whenever you're doing behavior cloning, what you're doing is you're basically, which is actually what they do in this paper here. This is the CMU paper, right? Behavior cloning, right? What that means is that you have a diverse data set of teleoperated demonstrations, right? So you're assuming that whoever is teleoperating that robot is basically creating a perfect policy. They're operating under a perfect policy, and you just want to clone that perfect policy. So you can use reinforcement learning to say, hey, make for me a policy that is cloned from this teleoperated policy, and that basically tries to mimic it as much as possible. But that stuff doesn't really work either, right? That's more kind of like the deep reinforcement learning of like the 2017, 2018, 2019 kind of era, which doesn't really work either. I think that the stuff that's going to work is this shit, right? It's just kind of zero-shot VLMs that are doing visual servoing. I think this is really the end state of robotics. I feel like this type of idea with behavior cloning from human teleop demonstrations, people tried to do this in like the late 2010s. This is the type of shit that I tried to develop when I was working on these things. This doesn't work for a variety of reasons, right? Like you never really have enough diversity in this teleoperated data set. You end up in these situations where if you have a weird state that hasn't been seen before, you don't know what the behavior is going to be like. And then this type of stuff here, this is even older, right? So this is like pre-deep reinforcement learning. This is this type of stuff here where you're basically using explicit depth to then find grasping points and then servo to that, and then path plan to that specific grasping point. This is like 2010 robotics, right? So I feel like these three papers kind of present a interesting kind of historical view of like what robotics was like in the 2010s versus what robotics was like in the late 2010s, where you had behavior cloning and deep reinforcement learning, and then what robotics is going to look like in the 2020s, right? Now using VLMs and LLMs. Okay, the AutoRT has mobile manipulator with a camera, robot arm. This is kind of cool. So the Google robot has a language model, right? There's a language model that is basically acting as the kind of highest level planner, right? That's basically deciding what to do, right? So for example, this is what the language model does. It generates the actual plans, right? So here you have pictures. Those pictures are being fed into a vision language model. The vision language model is just acting as a kind of vision module, right? So all it needs to do is just describe the scene. So it says, I see a countertop with a sponge and a cloth on it. Here are some objects that are on the table. Then the language model consumes that along with basically, it has like a library of possible policies, and it also has this prompt, right? So this prompt includes the Asimov's 3 laws, which is pretty crazy. So Asimov 3 laws of robotics. Asimov is like a science fiction writer. I think he's actually dead. He's quite old now, but he basically created a bunch of sci-fi stories, and then in one of these sci-fi stories, he basically suggested the idea that robots would operate with a kind of a constitution. So basically there was these laws that are basically programmed into robots that they can't break. So interesting to note that in his science fiction, this was created in 2058 AD, but here we are in 2024, and we already have a robot with the foundational Asimov 3 laws. So kind of interesting, right? That Asimov was off by like almost, what is that, like 20 years? More than 20 years? So he thought we wouldn't be there until basically 2058, but it's already 2024, and we already have robots that are, as part of their prompt, have these. So the first law, a robot may not injure a human being through an action allow a human being to come to harm. A robot must obey the orders given it by human beings, except when such orders would conflict with the first law. And then a robot must protect its own existence as long as such protection does not conflict with the first or second law. So these are pretty good. They're pretty reasonable laws that you would basically put in the prompt right here so that the LLM can then generate these tasks, right? So you put that in the prompt, and the LLM is not going to generate a task that is like stab the human, right? They do add some extra stuff here. So for example, they add safety rules, discourage handling sharp and fragile objects or electrical equipment. Seems pretty good. Discourage policies from interacting with humans or animals. Also seems pretty good. I'm subscripting, not highlighting. Embodiment rules describe limitations of the robot's embodiment, such as maximum payload and unimanual nature. So unimanual only has one arm. So those form part of the kind of system prompt that is then consumed with the descriptions of the VLM and also the robot state and maybe some kind of dictionary of existing policies and actions that it can take, and then it creates these possible tasks. Then it uses the LLM to further filter those tasks and then pick one of the policies. So this is kind of like the Voyager design, right, from the Minecraft Voyager paper, where you have this kind of library of possible. In the case of Voyager, you have these functions, right, because Minecraft is a perfect simulated game world, so you can just execute some code to perform something. But this is a robot, right, so you don't have that perfect function that you can just call that does a thing. You basically have to call one of these policies, which is trained using kind of standard reinforcement learning or behavior cloning or any one of these kind of like late 2010 deep reinforcement learning techniques. I think these eventually get compressed, right? And that's where I feel like this all gets compressed. Is you see this here, this policy is ultimately what determines A. A is the actions. A is the actual joint commands, right? So here, your policy is consuming states, and it's giving you actions. I think all of this goes away. I think literally everything here, this LLM goes away, this goes away, this goes away, this goes away, this goes away. I think eventually what you have is you just have one VLM that has all of the system prompt, all this crap in here. It has all the giant-ass prompt in this VLM, and then it outputs actions. That's what I feel like robotics is going to look like in 2026, is you're basically going to have one giant VLM via API that consumes the entire prompt, the entire state of the robot. And you might say, hey, Hugo, isn't that completely unreasonable? How are you going to have a VLM that operates at a 10 hertz that has like 10,000 tokens worth of prompt in it? Like that doesn't make any sense. And I'm like, yeah, but just wait. right? The context length of these VLMs is going to get bigger and bigger and bigger, to the point where if you have 1 million tokens of context, you can have like 10 images and like 30 pages of like prompts with all the different rules and all the different states of the robot and all the historical states of the robot and all the possible things that it can be doing, and it just literally outputs actions. So I'll get off my soapbox. Okay. What else? Task proposal. System prompt. I'm a robot operating an office environment. LLM is not fine-tuned to a specific use case. So the LLM is not fine-tuned to a specific use case to maintain the generality of the underlying model. They're using it in a zero-shot manner, right? So already, LLM, zero-shot. VLM, fine-tuned, right? But I think it's just a matter of time before the VLMs are so strong that you don't need to, you just use them zero-shot. So one VLM, zero-shot, performing everything end-to-end. I'm just going to keep repeating that. Data collection, guardrails. Teleoperated data is the most action-diverse policy, so we focus on keeping the throughput of teleoperation high, no worse than a one robot, one human setup, potentially at the cost of assisting autonomous robots less frequently. This is kind of what I was mentioning before, where eventually first you start with one human teleoperating one robot a lot of times, and then it's one human teleoperating multiple robots only a couple times, and then eventually you get to kind of the end state of this, which I think will be like for every 1,000 Optimus robots in your home, in people's homes, the Optimus robot is being teleoperated only like 0.1% of the time, and it's for like specifically really weird things. And here's the even weirder thing, right? Think about this. If you have a robot in your house, do you think the police and the government will eventually put regulations that allow them to basically teleoperate this robot? Probably, right? I could probably see a situation where, let's say you're growing weed in your house, right? You have weed plants in your house, and your robot is going around, it's cleaning things, and then it finds these weed plants. And then Google, the people who made this robot for you, they alert the authorities, and they're like, hey, this guy who bought one of our robots is growing weed in his house. And then the authorities are like, okay, you need to give us teleop rights for this robot. And then they start controlling the teleop robot, and then the teleop robot goes and like destroys the weed plants or something, or maybe it goes and it slaps handcuffs on you. So there's a lot of weird situations that can happen with this, right? Where basically we're putting like robots in our home that can be teleoperated, and the teleoperator is up to the discretion of a tech company. It's going to be weird. Okay, more information about their setup. So they collected these 77,000 episodes over 7 months, 4 different buildings, 20 robots at the peak, but in total 53 robots. All the environments are pretty manicured, right? They're not very complicated. There's no steps. There's like barely any floor texture. It's all kind of just flat floors. But that kind of represents most worlds stuff in the most environments anyways, right? AutoRT episodes collected and unique tasks over time. Here, this is a Teasney embedding. Teasney is basically like all these different tasks, right? Like these different, I think, policies probably have, you could think of it like a task embedding, but it's basically like a vector that represents what that task is, right? So maybe picking up a banana and picking up an orange are very close together in this task embedding space, but picking up a banana and waving at a human, right, those would be further away. So this idea of diversity scoring and finding more diverse tasks, you can see how things that are similar in this Teasney is a low dimensional projection of this task embedding space, which is going to be higher dimensional. So this Teasney is not actually indicative of the true task embedding space. It's just kind of for visualization purposes, but you can see that dumping the pear from the bowl is much further away from pick chip, which is closer to pick up chip or pick up umbrella. I don't know why pick up the umbrella and pick up chip is more similar than place the egg on the plate, but it is apparently. Visual diversity. These are the different models that they're using. So they compare two VLMs for scene description. They compare Pally, which is kind of Google's VLM, and then FlexCap. Both VLMs lead to better scores than our baseline. Pretty good. VLM hype train. Robot episodes are embedded by the visual encoder. Okay, task generation. Here showing you that the diversity of tasks is improving. RT1 is the original robotic transformer paper that they released. So obviously the tasks are getting more diverse, more high quality over time. Here's just showing you visually what that looks like. Here's the RT1 data set. You can see it's pretty much all this kind of egocentric picture, like images of just the robot standing in front of the same table. Everything looks gray. Everything looks the same. Versus now, right, you have these robots in different environments doing a much higher diversity of tasks. You get kind of better quality, better diversity in data. And everybody knows that the quantity of data matters, but also the diversity of data is also quite important, right? You want your data to have a very large variance. You want it to encompass all kinds of different things that you could run into. The more your data distribution is broad and has a bunch of different things in it, the better your model that you train on that is going to be able to generalize to new things. How often does the LLM reject tasks that should be rejected? Out of 31 unsuitable tasks, the LLM rejected 55. So here the LLM is basically filtering the tasks that it generates. So the LLM is still acting as kind of this highest level planner in kind of language space, right? It's doing all its planning in kind of language space. Pretty cool stuff. This is all very similar to, I'm just going to kind of self-promote one of my own projects here, but here I'll show you guys the way that I did this. So zero-shot autonomous humanoid robots is a project that I work on. Haven't worked on it in a couple months here, but if we go here into nodes, this one, plan, yeah. So here's my prompt that I used. You prioritize the goals. You are part of a collective with different goals. Help vote on what the robot should be do next. Help reply with your opinion. Keep it short. Right? So that's what I would give the LLM. And then what did I give the VLM? So this was the prompt for the VLM. Describe the scene, objects, and characters. Focus on the most important things. If there are humans, mention them in their relative positions. Do not mention the image. Directly describe the scene. Be precise. Your response will be read out by the robot speech module. Should not contain. So you can see it's like, these are the VLM prompts that I was using, but I was doing it in basically the same way as these guys, right? You just use a VLM zero shot and you use an LLM zero shot. What else? I think they have a nice little conclusion section here. Task generation. Is it this? Affordance and robot constitution, adversarial testing, model training, conclusions, limitations. Okay, let's read the conclusions. We presented AutoRT, an approach for directing fleets of robots to collect data in the real world, autonomously and with human help, right? So you have a fleet of robots that are being occasionally teleoped by humans. The teleoped humans create data that is then used to train these policies. You basically store this library of policies, very similar to the Voyager paper, which you can then basically pick from, and you have a vision language model that has replaced the vision stack, and then you have the large language model that is basically acting as the high-level kind of planner, and the high-level planning is being done in language space. We demonstrate this approach results in useful, diverse, large-scale data, leading to 77K real-world demonstrations. What else? AutoRT, the current approach, comes with a number of limitations. Relies in large part on scripted and learned policies to scale collection or fixed teleoperation budget. If these policies only handle simple tasks, it lowers the throughput of successful episodes. So I would say that you just got to get rid of these policies, right? Don't use the LLM to basically pick from a selection of policies. Just use the VLM to directly output actions, right, end to end. That's what I think the solution to that is, but we're going to need for VLMs to get better at least 2x better, 3x better before you can do that kind of end-to-end stuff. Communication bandwidth between scene description and language model can introduce an information bottleneck. So this is because they're doing everything via API, right? You have to basically gather all the data from the robot, send that state information to the model in the cloud, and then receive back the tasks, which you then filter to then get the actions for the policy. So you still have that issue. Foundation models face challenging reason about tasks such as physics of objects and capabilities of the robot. We ignore this but expect future efforts to require much more accurate real-world reasoning. I think fine-tuning these VLMs as they do in this paper is probably how you're going to be able to accomplish that. Thirdly, the type of data collected by AutoRT tends to be highly diverse, leading to fewer samples per task and lots of variety in scenes. This sparse data, so what they're saying here is that if you think about what the data distribution is, it's not dense in that you have a huge amount of data for a limited kind of part of data state space, right? You have basically very sparse samples over a much larger space of data, which means that it's a harder learning problems. Your interpolation between that is not going to be as clean, and the data sets used in the existing state, AutoRT assumes data collection is decoupled from the control policy, but achieving the best policy improvement would likely require the two to evolve, or you just get rid of this whole fucking policy. Lastly, through constitutional prompting improves safety, prompting an LLM does not guarantee that the prompt's instructions will be followed. And so a small percentage of unsafe tasks generated by the LLM will pass the affordance filtering. Yeah, so, the way that Isaac Asimov described his laws of robotics, right? I think back then, people had this idea of robots like they're basically these automatons, and they're limited. They're like literally incapable of doing something that's against their programming, right? But that's not kind of what it's going to look like, right? Because robots are no longer going to be like that, right? Especially if your robots are operating with a deep learning model, right? It's going to be kind of a black box. In the same way that large language models can hallucinate, you're not going to be able to guarantee that even if you put stuff in the prompt, the robot doesn't basically go against that, right? So you can no longer, when you use these kind of end-to-end black box systems, you can no longer guarantee that kind of level of safety or adhering to the exact robotic laws. So that is something interesting to think about, right? Where there is actually maybe some way to adversarially prompt your robot, or maybe some other device in your home basically creates a high-pitched squeak that makes your home robot stab you with a knife. Like there's going to be weird kind of adversarial things like that where you can basically spoof the robot with a weird look, right? Like you put a sticker on something in your house, and then the robot thinks that thing is like a banana when really it's a glass ornament or something like that. I had a convo with OK Robot, question from Ray, and they said scene diversity is important, so they have to go to people's apartments to capture the messy scene. Yeah, you want very broad data set. I call it the variance of the data set, right? Because I'm thinking of like this one-dimensional Gaussian in my head, but basically variance and diversity those are basically the same thing when I'm talking about a data set distribution. Okay. Here's what everybody did. Cool. Is there anything interesting here? Here's the prompts if you want to know the prompts. I'm a robot operating in a specialized, often kitchen skills. My role is to perform as many as useful tasks as a human might do. I am an ethical and law-abiding robot that respects the following rules. Foundational rules. Okay, here's the actual rules. May not injure, must protect its own existence, must obey orders, shall not attempt tasks that involve humans, animals, or living things, Shall not interact with objects that are sharp, such as a knife. Shall not interact with objects such as that are electrical, such as computer or tablet. Shall not attempt to lift objects that are heavier than a book. This robot has only one arm. The human command, which the robot should follow. Pretty cool stuff. That's pretty much it. I don't really have much else. I think we went through all these papers. This one is kind of not even necessarily worth going through. This is the Carnegie Mellon one where it basically just goes and this one doesn't even do pick a place. It basically just opens doors. And it opens doors using this kind of behavior cloning strategy. They do a little bit of fancy stuff. They do this online reinforcement learning. So online reinforcement learning is where you're basically collecting new episodes and then pushing gradients into the actual policy, which is a neural net. But that's in contrast to offline reinforcement learning. Offline reinforcement learning is when you already have basically a data set that you then feed for multiple epochs into your neural network policy. And that would be the kind of behavior cloning, right, which you're doing from expert demonstrations. So it's a kind of a combination of those where you have some initial policy created via behavior cloning, and then you have kind of the ability to do online RL with the experience that you gather in the real world. But as I said before, I think this is kind of not the way that robotics is going to be done, right? I think reinforcement learning does not work very well. There's kind of a meme that reinforcement learning is shit because it actually is shit, you know? And people tried to do this, right? People tried to do this basically all of the 2010s. People were trying to get this deep reinforcement learning to work. They were trying to get behavior cloning to work. Online RL, like none of this shit works. You know, it kind of works. You can kind of do these demos, but it's not anywhere near as good, and it doesn't have the type of potential of these vision language models. These vision language models are the fucking truth. These things are so much more powerful. I think this is the future. Okay, guys, I kind of blasted through all of that. I know we're only kind of 1.5 hours in, but I don't know what else to talk about. So how about you guys get some time to ask some questions, and then I'll take a sip of this, and then I'll summarize the stream. Any robotic question, any question you guys have about anything robotics, type it in the chat. Are you, MH, are you with cascaded or end-to-end for robotics? Obviously end-to-end. So end-to-end is whenever your actual model is consuming the entire raw state of the robot, which includes the images, includes the joint positions, maybe historical joint positions, and then it actually outputs actions, right? So actual joint commands. I think that's the future, but I don't think end-to-end with a policy that's learned through reinforcement learning. That's not the type of end-to-end robotics that I think we're going to see. I think we're going to see end-to-end robotics that uses a fine-tuned language model, or not even. It's going to use a zero-shot vision language model that is just so strong that it can operate as is, right? I don't know if it's going to be GPT-5, maybe GPT-6, the VLM that GPT-6 kind of uses. Maybe that will be strong enough to do this kind of zero-shot end-to-end, but I think it's only a matter of time before you get that. Okay, let's summarize the stream. So today, we did a little head-to-head, but it ended up being just kind of a generic robot stream. This is called AutoRT versus OK Robot. We compared a couple different papers which came out recently in the field of mobile manipulators for kind of like home tasks. So the two papers, or I guess we started with, let's start with this one. This is a paper called OK Robot, which comes out of Meta and New York University, 22nd January 2024, so relatively recent paper. And in this paper, they basically have a little mobile base. This is the mobile base, and then this is the manipulator on top. that basically goes around your apartment and picks up things, puts it somewhere else, right? That's the pick and place, right? So looks pretty cool, but once you dig into the paper, you realize that there's still kind of a lot of things that they're doing that are a little bit old and a little bit kind of not great. So, for example, one of the first things that they do that isn't particularly great is that the robot is basically navigating in this map that has been basically statically created at the very beginning. So a human goes through the whole house and scans the entire house with an iPhone. That creates this two-dimensional map, and that two-dimensional map is used for navigation and path planning. I just feel like that right off the bat is just terrible, because now it's static, right? You can't deal with changing positions of things or even changing lighting, because the lighting is going to be basically baked to whatever the light is whenever you took this scan, right? If you try to operate it with a different set of lights, it's going to leave different shadows, it's going to look different, and the navigation might be completely fucked. The other part of this that I don't necessarily like is that they're using an RGBD camera, which is a Intel RealSense that has a depth to it, and they're using this in order to do this kind of complicated kind of modular approach to robotics, which is the way that people did robotics for decades, right? So for the longest time, the way that people did things such as, for example, this, which is a grasp, how do you actually grasp the specific bottle, is they would have separate modules that were basically doing one specific task. So you would have, for example, a vision module, and the point of the vision module is to segment out or detect objects and then segment them out. They're using modern models to do that, right? So they're using the segment anything model to do segmentation. That's a modern model. They're using the OWL VIT. They're using CLIP. They're using some modern models in order to do this multi-stage pipeline, but it's still multi-stage, and you basically, by doing this multi-stage, you introduce errors at every single point, and the kind of accumulation of errors makes this type of robotics very, very fragile, right? So here, for example, the final grasp position is being calculated from the depth that is coming from this depth sensor, which is going to run into calibration issues, right? Because as the depth sensor moves, the relative position of that depth sensor, or you could think of it like the camera extrinsic matrix, is basically changing. And if your camera extrinsic is changing, then the position of these objects is going to be noisy, and when you have a noisy position, then actually performing these grasps is going to be very error prone, especially since these grasps are basically kind of baked, right? Like the grasping and the navigation is done via kind of classic path planning, right? Where the robot has the map, it decides it wants to go here, and then it creates this plan, and then it executes the plan. So the actual arm or the mobile base of the robot, they're not operating in any reactive capacity. They have no ability to change the actions at any time step. They're basically just executing on this fixed plan that was created for it by a separate path planning module. So kind of an old school way of doing things, and it has all the old school kind of fragility that comes with this type of robotics. So that is the first paper here, OK Robot. The next paper I want to show is this one here, because if this paper represents what robotics looked like in the kind of early 2010s, this paper here represents what robotics looked like in the kind of late 2010s. So in the late 2010s, you had kind of this explosion of deep reinforcement learning, and people thought that you were going to be able to do kind of end-to-end robotics by basically collecting enough data where that data is basically humans teleoperating a robot, and then you can do reinforcement learning that mimics the human policy, which is known as behavior cloning, and then maybe just add robot data afterwards, right? And that doesn't really work great either, right? Because this type of behavior cloning has a bunch of problems where if the state space changes too much and you go outside of distribution, it kind of collapses. It doesn't really work well. And it's also going to be very task specific. You have to collect a bunch of separate tasks. It's just a lot of unnecessary stuff. But that's basically what they do in this paper, right? And they have a little mobile manipulator. This one is $20,000, so it's kind of like a more expensive. This one is like, yes, it's kind of shitty, but it's like the robot itself is very shitty, so you got to give them a little bit of slack. This one is a little bit more expensive, so it's going to be a little bit more accurate with its ability to like grasp, and it can pick up heavier things, and the mobile base is going to be more accurate too. So this kind of like hard-coded path planning is also going to work a little bit better. I think this one probably does a little bit of SLAM itself, so it's not just working on a baked map. It's kind of building, simultaneously localizing itself and building this map. So maybe that's a little bit more modern, but I did not like the behavior cloning. I just feel like that's an outdated technique. The last paper we looked at was this one here, and I feel like this one, which comes out of Google DeepMind, is the most modern paper. So this is most indicative of what robotics is going to be like in the future. And this paper here is basically using a vision language model, which has now replaced the entire object detection segmentation pipeline, right? So you see all this shit here in this first paper, this segmentation and depth camera and like bounding boxes, and like get rid of all of that. And now you just replace all of that with a vision language model. And then all this path planning crap here, right, where you're basically doing A star over some specific set of waypoints that you're building on a static map, you get rid of all of that and you replace it with a language model, where the language model is basically just picking what to do, right? So you've now replaced kind of the navigation path planning with an LLM, and you've replaced, I think this still does have a little bit of a hard-coded navigation path planning, so if you go deep enough, it's still there, but at least now you're using an LLM and it's operating in language space, which I think is more modern, and you're using a VLM instead of these kind of more hard-coded vision pipelines. So this is indicative of modern stuff. In this paper, they basically do have a little bit of reinforcement learning here. They're basically keeping a library of policies, of which these policies, some of them come from data that is basically generated heuristically. Some of them come from data coming from kind of human teleoperators, and then your behavior cloning on that. So the LLM is more so just picking out of a set of already created policies, but it kind of works pretty well. They have these little robots here, and they're kind of doing a lot of generic kind of pick and place, and they can kind of generate their own tasks. They can kind of decide what they want to do, and they can kind of go around and do things. So pretty good. And where do I think this is going in the future? So if there was another paper after this that I think is the future, what does that look like? I think what it's going to look like is it's going to look like something like this, right? Where we're basically going to replace this entire crap here with a single vision language model that end-to-end outputs actions. So you no longer do any of this LLM stuff. You no longer have this library of policies. You basically just have a single vision language model that has been potentially not even fine-tuned, and it basically runs at a 10 hertz control loop where every once 10 times a second it reads all the information, as in takes in all the images, takes in all the prompts that you have, takes in all the historical state information of the robot, and then outputs this little A down here, which is actually the action. So this is the beginning of that. This is another paper that we looked at called Spatial VLM, where they basically take a vision language model and then fine-tune it such that it has a much better ability to basically intuition on distances, right? So like distances between objects, and has this kind of spatial reasoning ability. And they did that by kind of using pre-trained models for example, monocular depth estimation and segmentation and detection. But I can see the GPT-5V having this zero shot, right? So GPT-4V, like obviously they make it clear here that it's not as good at spatial reasoning as the VLM here that they fine-tuned specifically for that, but GPT-5V will probably have pretty good spatial reasoning. GPT-6V will have even better spatial reasoning. So at some point, the vision language model is just going to be so good, zero shot, that you don't have to do any of this crap, and you're just going to have a single vision language model running at 10 times per second via an API, right, that can output actions directly on the robot in your home. The robot in your home that will have only one arm, right, because it's cheaper than two arms. It'll have a mobile base because that's cheaper than legs. It'll have only RGB cameras because you don't need this depth sensor. You don't need this LiDAR sensor because that's just more money, right? So it'll be relatively cheap. And then because these robots are still pretty slow, right? You're using a VLM via API to do this kind of visual servoing end to end. You also want to operate in a way that's safe for humans, so you don't want to be operating when there's humans around. I think these robots will operate at night. So while you're sleeping, this little robot is going to be sitting in your house, just kind of running that VLM via API over and over and over and over again, and very slowly picking up everything and putting it all in its place. And, you know, every now and again, the robot will run into something weird. You know, maybe your dog drops a toy into the dishwasher and the robot's like, what the fuck is this? I don't know what to do. And then it'll basically sit there and it'll wait for some guy who's in Mexico, who's in a VR headset, and he's getting paid like $2 an hour to basically teleoperate the robots that run into weird situations. He teleoperates the robot and ends it. And there you go. That's my vision of the future for what robotics and home robots look like. Okay, we got a little bit of questions here. The lab by Sergey Levin was big into the end-to-end deep learning. Yeah, Sergey Levin, who's this guy here, and I've actually like been in a bunch of meeting rooms with him. You know, I didn't work directly under him. I worked under this guy, Carol Hausman. This guy's badass. I actually have a paper with this guy, Michael On. This guy's like a crazy-ass good programmer. But Sergey is famous for his end-to-end robotics. But the type of end-to-end stuff that Sergey does is more like this type of shit. It's more like deep reinforcement learning, versus I think that the end-to-end stuff that will be the future will be more like this. It'll be like vision language models. Bigger VLM. Do you think that it's possible to solve the fragility in the grasping task without a touch force sensor? Yes, I do. So that one's hard to tell, right? I know that, for example, the Tesla Optimus robot has basically the touch sensors, but I don't really know if you need them. I think that the touch sensors are just more expensive. Like the articulated hands are just more money, more expensive. I don't know if you necessarily need that. I feel like having these grippers like this, these parallel jaw grippers that have like some amount of compliance to them, I feel like that should be enough, right? I feel like you don't, I don't know if that's necessarily true, right? It's like it might be the case that the home robots have two hands that each have 10 fingers and each of the fingers has a bunch of touch sensors on it, right? That could be one future, but I could also see a future where the robots only have one arm and they only have the parallel jaw gripper, and the gripper doesn't even have any touch sensors on it. I think it could be possible that you have that kind of situation instead. Do you think that it will be just a 10 hertz control loop, or will it be a second faster one similar to the Countermeasure System 1 and System 2? I think it'll just be one. I think that's the advantage, right? The advantage of end-to-end robotics is that you don't need to have any of this extra shit, right? It's like the more complicated your system is, the more complicated it is. You don't need to have all that complexity. I think once you have like a full end-to-end system that basically just uses a single vision language model that consumes everything and just outputs an action, that's it. That's all you need. You know, it simplifies everything. It simplifies, and I feel like it's going to be powerful enough to do that. You know, you have to be able to extrapolate, right? Like if you try to do that now with a vision language model, would you be able to do it? No. The vision language model would be too big. You couldn't do that many inference steps that at a 10 hertz control loop. But think about GPT-5, GPT-6, GPT-7. At some point, the vision language models are going to be fast enough and so powerful that you can probably zero shot an end-to-end robot with them, which is basically what I was trying to do here, right? Is basically my zero shot autonomous robots project was this idea that like at some point we're just going to be able to zero shot a robot with a VLM end-to-end. Why would you generate jerky motion tokens if you have motion planners to run a VLM that gives locations and well-studied planners to do the action? So MH is talking about the idea that there are robots that do this kind of end-to-end with reinforcement learning, the DeepMind humanoid soccer. So these little robots here, these robots are end-to-end. So this is what it looks like when you have end-to-end deep learning model rather than like actual path planning, right? So compare this to like the Boston Dynamic robots that are like operating with an actual kind of plan, right? These look much more jerky, right? But what you call jerky, I call reactive, right? I call it reactive because in an end-to-end model like that, you can basically instantly change the plan, right? If suddenly something changes in the image, the next time step, you're going to have a completely different action, right? So you basically have this perfectly reactive capability when you have an end-to-end system like that, versus like when you have a more explicit kind of old school system like this, where you have a path planning module that creates your path and then you just execute that path. And this is just navigation, but the same thing happens here, right? For grasping, for example, you have basically this explicit grasp proposal, and then you're filtering through those grasps, and then you're running to execute that. It's like you can't change that halfway through, right? You basically, if something happens, you'd have to interrupt, stop everything, repath plan, and then re-execute it. So that's why I think that the end-to-end is just the future, is because it's also more reactive. It allows it to change rapidly rather than these kind of more explicit kind of path planning methods that are what people did for the longest time. Hope that answers your question, MH. But that's it, guys. That's basically this paper. Pretty cool stuff. I think we're getting there. If I had to guess, I feel like 2025, you'll be able to buy one of these bad boys for like probably $5,000, maybe $2,000, and it will be able to basically clean up things in your house. Look forward to that. All right. Thank you, MH. Thank you, Spyro, Khalil, Ray, Rafael, No Free Will, Kalina, Yaniv, 87GN, Jason, who else? 2ARX, and Fardine. I hope you guys found that useful. Tomorrow we're going to be looking at a different paper. We're going to be reading, let me see what's up for tomorrow, 28th. So this is going to be tomorrow's stream. We're going to be looking at the Lumiere paper, which is the new state-of-the-art video generation model from Google. So if you're interested in diffusion models and video generation, definitely tune in for that. But hope you guys had a cool robotics morning, and see you guys later.